Oh, hi everyone. I'm back again to prove one more set of formulas for integrals. The last time made two videos. One was why integral secant is ln secant plus tan, and that one. We also seen integral of cosecant is ln of cosecant x minus cot x. And this time, I'm gonna make quick videos. Like to prove why integral of, so you have a 1 over quadratic form where the linear term is missing, you have a quadratic and a constant. So I'm going to go straight away to the first one. So here it is, a. So y integral of x squared plus a squared is this. So in this case, I'm going to use a substitution method. So substitute. So what are we going to substitute? So in place of x, we replace x equals, and there is a 1 plus 10, back of our mind we should know that Pythagorean formula that tan squared theta is secant squared theta. We are going to also use secant squared theta minus 1 is tan squared theta. We also need to know that if you have 1 over pq, this is same as 1 over q minus p, and 1 over p minus 1 over q. Or you can also write this as pq is q plus p, and that if you write plus, then it is p plus 1 over q. So this is what we are gonna use, and you can always check this whether this is true, because you multiply QQ, you multiply PP, and then you try to get the same denominator, and this will be Q minus P. So Q minus P will cross out with this one, and you end up getting the PQ in the denominator. The same thing. Let's check it out. Substitute is A tan theta. So if I plug in x equals a tan theta, then remember you take the derivative of this. So dx equals, and the derivative of tan is secant squared theta times d theta. See, so we have to replace that dx by a secant squared. But then if I divide this by a, because in the later steps we need this, so tan theta is also equals x over a. It means theta is tan inverse of x over a. So these are the requirements. Let's move here. So that means I need to replace dx is replaced by a secant. So this is going to be a secant square. So I will call this as I. So that I is integral of a secant square theta divide by, so this I will put theta, d theta right here, and x is replaced by a tan theta. So because of the square, so this will be a square tan square theta and plus a square. Then we can undo distributive property and see there's a square both places. So we can undo, apply distributive property. This will be a square out, pull out, and what stays inside is tan square plus 1. And then 1 plus tan square by Pythagorean formula is secant square, so I'll replace this, and then this one of the a will cross out because singly this a can be pulled out and write 1 over a, and you have secant square theta divided by 1 plus tan square is secant square theta, and clearly this is the same thing. So what are you left is integral of 1 d theta. And what is integral of 1? Whose derivative is 1? It's theta plus c, right? But what is theta from here? So theta is, you replace here. So the integral of 1 over a square plus x squared dx is There's a 1 over a right here, which I misstated. So that's 1 over a. So this is 1 over a. Okay. So this answer is 1 over a times tan inverse of x over a plus c. And that completes. We can give so many examples. We can apply this, and I can just write one example of if it is one integral of 7 plus x squared dx. So how do we find the entire derivative of this? So you just write integral of 7 can be written as square root of 7 square plus x squared. So the a, this is a is square root of 7, so 1 over a, so this is how we write down, and you get tan inverse of x divided by plus c. So this is just an application. We can have so many problems. Now let me go directly and do the second one. What if it were? So I'm going to use two methods. One is using this trick I'm going to use. So that's the fastest way to get if I use this one, 1 over PQ. And let's see what is P and what is Q. Or the second method we could use is substitution. So let's see what substitution can we do there. Okay, so let's see. So if this was minus, right? So let's see if it is minus. And how do I go about and figuring out what's the integral of this? So let me use method 1. So the method 1 is, I will write here method 1 is using this tree. Now first we can write this integral as I equals 1 over x minus a into x plus a. So this is difference of square, right? So the difference of square, if we have x minus a, x plus a, the same as x squared minus a squared, using the difference of square formula, which is a squared minus b squared is a minus b, a plus b. So what I did was I did go backwards to get that. So if you have product of the binomial, you can write it as the minus and the plus. But with same AB, you can always write a square minus b square and add that. Now this is, I'm going to use this p. So the p here is, the p is this one and the q is this one, right? I can use this as 1 over q minus p and 1 over p minus 1 over q. So this will be I equals 1 over q minus the p. Let's see why we do this. And then integral 1 over xp, that is x minus a, and minus 1 over x plus a. And this whole thing dx. Okay. Now, so let's open this. So when you open this, this becomes, this will be minus x. So this minus x and this will cross out. And this negative and this negative change to positive. So you have two a's. So I equals 1 over 2a integral. And here there are two parts, a and minus b. So I will write it separate. 1 for integral 1 over x minus a dx minus again integral 1 over x minus a dx. Is that correct? Okay, check it out. And then you do know what is the value for this. What's integral of, so integral of 1 over x is ln of x, right? So here it is x minus a, and because the derivative of the denominator, so if you take the derivative of the denominator x minus a, it's 1. So we can directly write it as 1 over 2a ln of x minus a minus, again the same thing, the derivative of down is up, so we can directly write ln of, I think that is plus here, plus c, and then plus c. Now by laws of logarithm, ln of m minus ln of n, you just divide the 2 and you get the answer 1 over 2a. So get ln of x minus a, and then x plus a plus c, and you're done. Now this is using the trick, but is there another, can we do it without this? So let's see the method 2 is using substitution. Remember, if you have 1 plus, if you have this form, let's see, if you have something like a constant square, let's see, there is a square and there is the variables x here, I think. It's better to substitute x equals a tan theta, but if it is x squared minus a squared, you better substitute x equals a secant, okay? And if it is a squared minus an x squared, then it's better to substitute x equals a sine theta. These are most important substitution that we need to know. So let's see, in this example I'm going to use, we want to know, let's substitute x. In this case, you see this, we can substitute x is a secant theta, right? So if I take the derivative of this, dx is a derivative of secant, the secant tangent, right? D theta. So let's replace that. At the same time, we're gonna write this as x divided by a is secant theta. Okay. Now what is this? Why do we need this? Is this is same as cosine theta is, because secant is the reciprocal of cosine. So this x over a is a over x, and then we can draw a triangle. The adjacent, cosine is the adjacent, so this is the a, and the hypotenuse, so that's the adjacent, and that's the hypotenuse, and then the right triangle, this is x, and that is a squared. This becomes hypotenuse squared minus a squared. So we can do that directly. Of course, you can always see, if you don't know what is that, then okay, you write a squared, and you don't know whatever that is equals x squared, right? And you subtract a squared. So this goes away and you get x squared minus a squared, and you take off this and you put a square, you get that. Okay, now from here, so the integral, the equivalent form will be dx, so this x is replaced right here. So let me write and this is because it is a secant and the square, so it's a secant square theta minus a square and d theta. Okay. Now look at it. Again, the same thing. You undo this, so we'll take it out. So when I take it out, I just take this off and put a parenthesis, and you get 1 here. So I'm just going to skip that step to show that you undo distributive property, and you can see there's a and there's a square, so this a and this one of the a goes away. You can write 1 over a integral secant theta tan theta, and the secant square minus 1. So I'm going to use this Pythagorean here identity as like tan square. So we have one, there's a single tan theta, there are 2 of them, so one of them goes away. So you get secant over 10, and the secant over 10 we can write as 1 over cosine theta. 10 is sine over cosine theta. And both have the same denominators. You see this, there's cosine, cosine. So we can use the shortcut trick. If you have A over C and you have B over C, instead of writing down keep, change, flip, in other words, this will go as a numerator, this will go as a denominator. So you can just cross this out and get A over B. So that's what I'm going to do. This cosine goes away. And then we get, there's 1 over sine. So, and what is 1 over sine? So you get, so this will be, this is like 1 over A into 1 over sine. And 1 over sine is going to be cosecant. So the whole thing reduces to 1 over A cosecant of theta. And from the earlier, the integral of cosecant, you can use ln of cosecant minus cot. So that will be 1 over A ln of cosecant theta minus cotangent theta plus C, right? Then one more thing is, we are going to use this triangle. This is the theta, because secant is x over A, so this is important. From here, using this, we got this form. Now we have to use directly substitute in terms of x. So this is 1 over A ln cosecant. Now what is cosecant from here? It's the reciprocal of sine, right? Sine is opposite, well, that's the opposite, that's the hypotenuse, that's the adjacent, right? So opposite over hypotenuse, but cosecant is hypotenuse over opposite, so it's x, so x divided by, so hypotenuse over opposite, x squared minus a squared, minus, and what is cotangent is reciprocal of 10. 10 is opposite adjacent, so cotangent is adjacent over opposite, so that will be A divided by, okay. Then, both have the same denominator and you can write the numerator exactly the same. So x minus A, so it's going to be x minus A. We can, okay, let me write that step, x minus A divided by and root of x. We can use the difference of square, the denominator can be written as, so we are almost there. This is same as difference of square, x minus A, x plus A, and at the same time we can write two of them, one is x minus A, so x plus A, right? So I skipped one step here to show that it is square root of x squared minus a squared is x minus a plus, so, and then you separate the square root and write twice. You distribute the square root. And the numerator we can write x minus a. We can use that if we have a is same as square root of a times square root of a. So we try to manipulate equivalent form to write. What is the reason is, this could be written as square root of x minus a and square root of x minus a. And one of them goes away. What did I do here? Okay, this. And you can see this stays. Both have a square root, so I'll write only once. So this will be ln of square root of x minus a over x plus a. So using the common square root for both numerator and denominator. And then we can use the definition of square root raised to half. So I don't have enough room. Let me write it right here. So we did this. Okay, I'm just ending this proof. So this equals 1 over a ln, now remember there's a square root, I can write it as x minus a over x plus a raised to, so I can put it this way because you can put raised to half, right? So this is it's a, because of the definition, right? You can write equivalent form square root of b is same as b raised to half. That's all I'm doing. Now this half is same as taking outside. Now use the laws of logarithm says if we have logarithm mn to the base b is same as n logarithm of n. So we will use that part. We'll use that formula and say, hey, that half multiplies right here. So that's like 1 over a times this half will go right here. And we're left with ln of x minus a over x plus a plus c. So I think I forget to write a plus c. Everywhere should be c constant of integration. Okay, so we almost, and then finally it is 1 over 2a ln of x minus a x plus a plus c, and you're done. Okay, so lot of steps. Look at that way. We started from there, substituted, and all this work just to get that. Now, if the question is asked, how do you know this? You can do the same substitution here. In this case, you're going to substitute x equals a sine theta. So last time I substitute the secant, but this time you're going to use sine theta, and you end up getting the same thing. So I'll just leave it for you guys to do, but it's the same idea. Only thing I'm going to substitute this way, or if this question is asked, we write I is integral 1 over a square minus x square. The first thing is you change the order. So if you change the order, so this I will be is minus, and this will be x square minus a square. See, and then you prove this part. So and then this answer is right here. So so this is minus ln. So I equals minus, this part we already know from here, which is 1 over 2a ln x minus a x plus a plus c. And then because of this minus, it's like this is exactly like a minus 1, and we can write this negative 1, we can take it up here using laws of logarithm. So what stays is 1 over 2a will stay, and you get ln of x minus a x plus a raised to minus 1. So what is this minus 1 means? You take the reciprocal of this one. So you get 1 over 2a ln x plus a. Now I'm going to write it like a plus x, okay? And it doesn't matter. This flips. And x minus a or a minus x is one and the same because of there's an absolute value sign, so we can always change the order. So absolute value is, if I have a minus b, is same as b minus a. So like a universal way we write, if it is given to you a square minus x square, then it is a plus x and a minus x. That's all it is supposed to do. So my aim for this was to make this video as why this formula exists. So the goal of making a lot of videos is to prove how did these formulas come from. Like in this example, we will, if there is a question or example of integral of 1 over 9 minus x squared. So what is this answer? So you're going to write 3 squared minus x squared, and x, the a is 3 here, right? So the formula is that is ln, you just put 1 over 2a, so 1 over 2 times the 3 is the 3 which is right here, and ln of a plus x, so it is 3 plus x over 3 minus x, and you're done. So that's all it is. So easy. Problems are easy. So a lot of students do a lot of thousands of problems, but do we know how to arrive at these proofs? Why these formulas? So next set I'm going to prove is to show you another group of formulas, and that will be integral of 1 square root of x square minus a square, 1 is x square plus a square, and integral of 1 over a square minus x, so with the radical sign. So the one that we did was without a radical sign, but what if there is a radical sign, and there's another. So two more videos will be shown, one for this will be one group, and then another group will be integral x square plus a square, integral. So this is one more set of groups that we need to know, okay? So thanks for watching. If you like this, if you are interested to know why the formula exists, this will be a good playlist for you. Just to feel good. Solving is easy. It's so easy to apply those formulas. See, this is everybody does this, but does everybody know how do you get the formula? Okay. So thank you for watching. If you like this video, if you appreciate what I'm trying to show, please just click on the like button and share with a lot of your friends, and that's all I want to do. So I feel to share whatever I know, maybe because when I was a student, I always wanted to know why the formulas, where the hell you get these formulas from, and that's what I'm trying to do. Thank you for watching, and do share with your friends, and click the like button. Thank you, and do write comments also.